All right. So next is the final paper of this session, which would be presented by Professor Shen Dian from Southeast University. And he will talk about enhancing network traffic prediction by integrating graph transformer with the temporal model.
Okay, thank you. I'm Dian Shen from Southeast University. Today I'm on behalf of the first and second author to be here to present our paper entitled as Enhancing Network Traffic Prediction by Integrating Graph Transformer. This paper is purely about AI algorithm and how it applies into network. So with the rapid advancement of network technologies, it is crucial or fundamental critical to accurately predict the network traffic because it is critical for resource allocation, load balance strategies, or network security. So actually, to predict the network traffic has a very long story. Traditionally, when we use the statistical approach, such as ARIMA, they are well known to be useful for sequential and seasonal time series prediction, but they are also well known to be not so accurate when tackling with nonlinear network feature relations, particularly in large-scale heterogeneous and complex network environments. So more recently, there have deep learning based methods which show that the effectiveness and their application in network traffic prediction. Some representative methods include RNN and their variant like LSTM and GRU. Although this approach can capture the temporal dependency or the traffic trend much better, they cannot tackle with the spatial interactions. So actually in network, the spatial actually is more important because it naturally have network topologies, and the network traffic on the topologies usually have some latent dependencies. So actually if we want to predict the traffic, we want to incorporate these latent features like spatial correlations. So to model and capture the topologies features of networks, recent research like GNN come into our mind. So we are asked how can we use GNN-based method to capture the spatial modeling in traffic prediction. However, traditional GNN-based method works by aggregating the information from the neighborhood nodes with one hop or more. They cannot effectively capture the latent spatial correlations between node pairs that lack direct physical links, like this, like the V1 and V5 in this picture. Although they have not directly connected, but they have some latent space correlations because usually in computer networks, there are many like synchronization or collaboration in distributed communication or computing. So even not they are directly connected, they have some feature correlations due to in this network. So to conclude, all existing methods have their limitations. So we want to design end-to-end matrix prediction methods that can extract spatial features from the data and establish a connection between node pairs that even they do not have some direct physical links. So first, we look back at the network traffic prediction problem. It is actually can be modeled as this picture shows. We are given a series of history traffic matrices, and we want to predict the future traffic matrices for certain steps, usually tens of steps. So what we do is to use a new kind of model. It's called Graphormer. Actually, it's kind of transformer algorithm to combine with a graph. So Graphormer is a model that proposed 3 years ago This one is relatively new because it hasn't been applied into the network traffic prediction. Actually, at first we want to try this method. So after we try, we find that the Graphormer, this algorithm, can leveraging the superior global perspective of the whole network and can extract some spatial features from data. So it can establish connections between node pairs, and so we think that it can augmenting the temporal nodes capacity to extract some temporal features. For example, you can see that the blue matrix here is a spatial encoding generated by the Graphormer, this method. We can combine it with the edge encoding. So edge encoding is actually the physical topology. It is represented by the edge encoding. So we can fuse these features together so to enhance the network prediction. And we can also use these features along with some temporal prediction methods, so they can enhance the temporal model fidelity. So there are some details of our method. The overview of this method can be seen here. Before we use this Graphormer, we have to be first, we use a dynamic agent module. It is responsible for converting the traffic matrix into a weighted graph. Then the weighted graph is combined with the spatial encoder and the centrality encoder to further process this weighted graph and pass the weights to the transformer for future calculation. So in the overall procedure, besides the transformer itself, there are some other learnable parameters such here. These parameters are learned in the training process. As an example here, the learnable encoder f theta generates edge weights proportional to real-time traffic intensity, allowing dynamic adjustment of the neighborhood influence based on the current network conditions. And also, there is also a learnable parameter alpha. We use this in or out degree measures as a centrality encodings, capturing the involving node importance. So if this node is more important, they have much more attention in the features calculation. And this learnable fusion parameter alpha automatically balances the relative importance of incoming and outgoing traffic flows. This is also trainable, some MLP modules here. It can abstract the edge features from the raw traffic weights to the intermediate representation and finally to the attention head dimensions. This encoder is shared in all time steps, so it can ensure stable future extraction patterns. So this one is shared in all the training steps. After that, we evaluate our method with some open source data sets and compared with some representative algorithms. The data set we use here includes some representative network traffic consists of tens of nodes and tens of links. And we compare our method with some AI-based methods such as TCN, LSTM, and our method, Graphormer, can be integrated with all the above time series prediction methods. So it is pluggable to this method. So this is interesting experiment result. We can see that all this method, if we use the traditional only time series based method, the error rate is relatively high. After they combine with our Graphormer based, all the methods can improve their accuracy. But we find that the GRU method performs much better when combined with our Graphormer, even though that the GRU method is not the best in the previously, but when it combines with Graphormer, it performs better than other methods. From our analysis, the improvement stems from we capturing the real-time traffic correlations between the nodes, even though they are not directly connected. So we can say that our Graphormer can capture the spatial spatial relationships among the nodes. And also the preserving network topology structures, so it can actually have some good results when predicting the traffic. Also, we test our method to the long-term accuracy, which means that we predict many steps after the actual traffic. Well, we also find that we can predict even 200 steps beyond our proposed method can still maintain a very low error rate, so it can exhibits a remarkable resistance to error accumulation. So that's all of our method. Our method is actually an AI-based method. We want to try it to use it to the network traffic prediction. Actually, it's a very first step. We find that many AI-based methods can use into network problems. So that's all for my presentation today. Thank you.
Thanks, Professor Shen, for the inspiring talk. Are there any questions? So I have a question. So I think previously there were some studies that try to leverage like GNN,
Yes.
graph neural networks,
Yes.
for network traffic prediction. So how is this, what's it called? How is it different from GNN-based solutions?
Yes, actually I mentioned here, GNN is very first, is a natural way that we can model the spatial relations among nodes, but they cannot model the nodes that are not directly connected, because the GNN models is working by aggregating the node with one hop or another and aggregating the features together. So if they are not directly connected, usually they are missing some information here. So we use the Graphormer. It will have the transformer will have more global view of all the topologies. So even though they are not directly connected, they maybe have some data correlations among the traffic. So we can better use that features.
I see. Thank you. But do you have any evaluation showing that in some scenarios that Graphormer is better than GNN?
Yeah, that's a very good suggestion. We can do some experiments.
Okay. Thank you.
Thank you.
Okay. Oh, sorry. Please go ahead.
One of your topologies seems to not get that much improvement compared to the other two. What's the reason that the GANT topology doesn't give you as good an improvement in the MSE? Go to your tables.
Okay. You mean,
what is the reason that the middle topology seems to have such a hard time getting improvement?
you mean which one?
GEANT. What is the characteristic of that topology that makes it hard?
You mean why is topology makes it hard? I think this is the traditional method. Does not consider the topology information. For example, the TCN, it will treat the traffic matrix like so. What? Sorry.
I'll talk to you after.
Okay. Thank you.
Okay, thank you. And that concludes the talk, and we'll have a short coffee break until 11:10. Thank you.